test, 1, 2, 3. It's a little bit not that. Wow, let me just raise it up a bit. -5 decibels. 1, 2, 3. Yeah. Alright, that should be good. Let me share this to everyone. Alright. I am now live on my channel, continuing my kernel dev. Hello world. Okay, so hello everyone. We are back with our kernel development live stream that I decided to make because I wanted to record everything. Let me pop out this chat so I can see if anyone's typing something. Oh, no, but okay. So what I prepared for today is this paper right here. This is the calling convention for the RISC-V standards. C compiler standards for RISC-V 32 and RISC-V 64 programs. Yeah, so this one includes like things like registers and C type. Oh, and then there's also the registers over here. So I don't have to like have this tab open all the time. Though it would be nice if I could have a whole book of the RISC-V. What do you call it? RISC-V like specs. I think that would be better. So this is my social media. Right. Okay. So let's continue. Let me just check if something's good. Someone commented. All right, we'll start in a bit. Okay, Facebook. See what's going on over here. Okay. All right. So, I don't think there's anyone watching. That's all right, because this is not supposed to be. I did not intend this to be public at all, but since some people are interested in it, I decided, you know what? Yeah, sure, we can make this public, right? Okay, so let's continue. So what we have done so far is boot up a kernel that will have a kernel that boots up, right? And just runs on an infinite boot loop, which is great for us. And what we will need to do now is to print hello world onto the screen. Okay. Now, if I could, I would probably prefer. Is it preferable to use micro for editing? It's like the file. I don't really do. I mean, is it? I'm not sure. Anyway, it's fine. Or maybe VS Code. Yeah, VS Code is fine. Not like sure I could use micro, but since I have an editor, just use the editor, right? Okay, so yeah, there you go. So let's go to hello world. We're gonna follow. So here it says in the previous chapter we successfully booted our kernel. Although we could confirm it works by reading the register dump, it was somewhat unsatisfactory. That's correct, because it just boot loop because of this for loop over here, which is it's a loop for loop anyway, an infinite loop. So today we're gonna output a string to the kernel. Okay, here. So it says in the previous chapter we learned that an SBI, SBI is I always forget what the word SBI actually means. Let me close this out. SBI. Oh yeah, supervisor binary interface. API for OS kernels. Yeah. So here it says to call the SBI to use its function, calling the supervisor binary interface, we're gonna use the eCall function apparently. So it says, okay, so first it includes the kernel.h. So let's write a kernel.h first. Kernel.h is apparently it's a return value structure. Yeah, that makes sense. So it's pragma 1. I wonder what this is. Does it say? No, it doesn't say. Yeah, okay. So struct SBI ret or return SBI return long. This is a type. If we look here at the calling conventions, long is a long integer. For RV32, RISC-V32, it is a long integer which is 4 bytes long. Yeah. So 4 bytes. There you go. Right. And then long value, and then we add a. There you go. So now we have our own return structure, right? Okay. So here it says create a new kernel LH and define the return value instruction. All right. And so what it's asking us to do. So this is in the kernel.c. We are supposed to we're supposed to include it as a header. Well, it's a header file after all. Then the hold on, I'm not sure what this is about. Okay. Okay, let's play some music actually. Why code? Because I think it's the best for me to do this. But I'm listening to some music. You know, it's nice for me. Okay. So, I'm not sure. I will keep this here because we're probably gonna use it anyway, right? So, memset. Okay. So apparently memset. So we're not gonna use memset here apparently. But instead we're gonna use the put character function. So what we're gonna do here is I'm gonna make a section over here. Right, this is the week 2. So we're gonna make a struct. Function. I think. Yeah, it is a function that has SBI call. So it's a function that's called supervisor binary interface. You know, SBI supervisor binary interface. SBI call, and we're gonna have a bunch of arguments. Actually, now that I've thought of it. Function. So the parameters are variable in the method definition. When a method is called, the arguments are there we pass. Oh, okay. So the parameter. So we're calling the. So this part here is the parameters. Okay, sorry, I forget. So long arg0, long arg1. I don't know if I should write it this way. Curly brackets. And then long arg1, long arg2, long something like that. Oh, so it's like long arg3, long arg4, long arg5, long FID. I'm not. I think that'll be. I'll explain what that is. There we go. Now, we're gonna say register, which is apparently a C keyword. Because I think that so it's basically a register, right? A0 dot equals arg0. And I think we can just copy and paste that in. Yeah, and then we change this. 1, 2, 3, 4, 6. Okay. And yeah. Oh, okay. So we're basically We're basically giving it a register. We're basically like, what do you call it? Defining the registers that we're gonna use here, right? 3, 4, 5, 6, 7. Oh, sorry. FID and then EID, right? Okay. So the FID. I could write it up here, actually, because I think it's a lot better to do it that way. So the FID terms I should know. So the FID is the SPI function ID, and the EID is the SPI extension ID. Right. So we'll look into the explanations later. We're gonna write this code first. So assembly, volatile. So this is the syntax that we use to write inline assembly, right? Oh, volatile. Sorry. E call, and then R A0 okay, let's put that A0 and then comma R and then A1 and then I'm not sure, hold on, R equals R A0 and then R A1 then A2 A3 and then oh wow 3 A4 oh my god. Oh, A5. Hopefully today's thing's gonna be not that long. I'll probably have to sleep soon. I'm too tired. A7. There you go. Then memory. Okay. So if we go back here, this function will return struct sorry, we're gonna cast this error, dot error equals A0, and then dot value is equals to A1. Yeah. Yes, yeah. Oh, yeah, yeah. We're basically no, sorry, no. It's not. It's not. What? I mean, could it be? It's casting. It's not a casting, is it? Because we're basically like we're basically setting like returning a well. It is returning a struct that has this data in it. Okay. All right. So that is the SBI call. We're calling function SBI call function that calls the supervisor binary interface. Yeah. eCall function. So apparently it's an eCall function. Yeah, this is it. So we're gonna use. Okay. So kernel main. Kernel main. We're gonna write a function first. We're gonna write a function called put character, which is actually something that is specified in the standard C library. Yeah, because it does exist. If you go to standard, if you include right standard input output, there is a function for putting characters to your screen. I'm not sure. Yeah, something like that. Oh, we have one viewer. Hello, whoever's watching. Nice to see you. I am writing something. Anyway, so character 0, 0, 0, 0, 0, 0. How many zeros? 6 zeros and then 1. This is apparently a console. Okay, so this is put character. Console put character. Interesting. A0. Oh, the reason why it's A0 is because yeah. Right. So, if we look, right, A0s are the ABI name because A0 we're using A0 to 7. They are the registers X10 to X10 to X17, and these are function arguments. So function args and return values. So A1, A0 to 1, A0 to A7 are function arguments, return function arguments, and it corresponds to X10 to X17 registers of 65. Yeah, so these are basically function arguments. Oh, that makes sense now. Because you see, right? This is the actual function, right? These are basically its arguments. Oh, okay. All right. I see. That's why. This is why you gotta have this in hand, right? The calling convention. Yeah, this is good. Yeah, we gotta refer to this a lot. Yes. So, put character. Yeah, that makes total sense to me. Yes, we're basically because like A7, we're putting it in the A7 put. So it's like eCall, and then the argument, the last argument is like 1. Okay. All right. So what we're gonna be doing is we're gonna get rid of this allegedly. I'll probably just comment it out for now because I do not want to remove anything that I need. So we're gonna use a constant. Okay, we're gonna declare a constant characters, basically a string. We're defining a string, right? But we don't specify the size because this is also another way. It's basically like a pointer to a pointer to, because if you do s, if you print an argument, if you print out the address of s, it will be the memory address of the first character, I think, and then yeah, something like that. Alright, so hello. This is two new line characters, so we'll probably have two new lines, and then hello world, and then backslash n, and then semicolon, and we're gonna do for. So this is gonna be a for loop. So for I is integer I is equals to 0, and s is oh yeah, because we're looping. Sorry, yeah, we're looping through the string. Yes, because the s because the string is technically an array of characters, right? That's how C works, right? A string is an array of characters, and what we're doing is we're looping through this, right? And as long as the character, okay, or the index of this is not equal to the null character, terminating null terminator, then increase I, increment I, and then we're going to put character, right? Put the, so as it goes through the string here, right? No, I do not want chat, please. We're basically looping through the string so that we can print each character, right? So we're looping through all of it, and then we're looping, let's say, okay, so it goes to the first character, first byte, because according to the RISC-V calling convention, a character is 1 byte. So a null terminator, a new line character is 1 byte. So we go through that first byte. First byte is 8 bits. So first byte, we print the new line character, and then we print the next new line character, and then we print HELLO space WORLD, right? That's how it works. Yeah, that's how this thing works, really. And then we have our for loop, in which it is another inline assembly, volatile. Not sure what WFI means. We'll figure it out. Volatile. What did I write wrong? Expected a. Yeah, it is there. What? Oh, sorry. There's supposed to be a double what do you call it? Underscores. So we've newly added an SBI call function. This function is designed to call OpenSBI as specified in the SBI specification. The specific calling convention is as follows. Oh, here we go. All SBI functions share a single binary coding, which facilitates the mixing of SBI extensions. The SBI specification follows the below calling convention. An eCall is used as a control transfer instruction between the supervisor and the SEE. I have no idea what the SEE is. A7 encodes the SBI extension ID. A6 encodes the SBI function ID, or given extension ID for given extension ID encoded in A7 for SBI extension defined in or after SBI v0.2. All registers except A0 and A1 must be preserved across an SBI call by the callee. All registers except must be preserved across an SBI. Yeah, okay. SBI functions must return a pair of values in A0 and A1. Oh, so this is exactly what it's about. Yeah, there you go. With A0 returning error code, there you go. And this is analogous to returning the instruction. Yeah, there you go. Good. Which is, that means that callee must not change the values of except A0 and A1. In other words, from the kernel's perspective, it is guaranteed that registers A2 to A7 will remain the same after the call. Yeah, that's correct, because according to this, right, A0 to 1 are return values. Even in the calling convention, it says that it is a registers that's also for return values. So A2 to A7 is basically function arguments. Okay, so register and register name used in each local variable. Declaration asking compiler to place values in the specified. Oh, that's cool. So, these functions register ask the compiler to place values in specified registers. Cool. This is a common idiom in a system call invocations. Yeah. Oh boy, system calls. Yeah, there you go. Oh, look at that. Look at that beauty. You see that? You're just storing shit. You're just storing shit in the freaking registers. It's that simple, yeah? This is what? RISC-V syscall architecture. Yeah. It's that simple, is it? Okay. So, after preparing the arguments, the eCall instruction is executed in the inline assembly. Where is it? Yes. When this is called, the CPU's execution mode switches from kernel mode to open SBI mode. So S mode to M mode. M mode is the BIOS, basically. And open SBI's processing handler is invoked. Once it's done, it switches back to kernel mode and execution resumes after the eCall function. The eCall instruction is also used when applications call the kernel, system calls. The instruction behaves like a function call to the more privileged CPU mode. To display characters, we can use console put char function, which is this one apparently. When write data in the spell console, the console gets char. This is me will block if there remain any pending characters and transmitted. Return 0 success. Yeah, there you go. Console put character is a function that outputs the character passes and arguments in the debug console. Okay, so try it out. Let's try our implementation. You should see hello world if it works. Cool. So let's try it out. We have our terminal here, right? And what we'll do is we'll do run. Hey, look at that! Look at that! I did it! Whoa! I did it! So what I just did is that I just called. Okay, so list live hello world. When SBI is called, we just called a supervisor binary interface. Characters will be displayed as follows. The kernel executes the eCall instruction. The CPU jumps to the M mode trap handler, which is the MV register, which is set by the OpenSBI during startup. Now, after saving the registers, the trap handler written in C is called. Based on the EID, the corresponding SBI processing function is called. The device driver, which is sends the character to QEMU. This is a device driver. Oh my goodness, they have a whole ass freaking driver for this. God damn, look at that. Yeah, I actually want to know how to write drivers. I'll figure it out somehow. QEMU 8250 UR emulation and implementation receives the character, right, and sends it to the standard output. The terminal emulator displays the character. That's by calling for yeah. It's not a magic at all. It just uses the device driver. Oh my gosh! Wow. Let me put this on Fetty. This is great. Oh my god. Yo! I just printed hello world using OpenSBI device UR18 device drivers. Woo! Reply. Yeah. See? This is how fun this is. You get to learn, right, how this whole thing works. Right? You're basically the kernel executes eCall, CPU jumps into BIOS mode, and then CPU like jumps to the BIOS mode trap handler, and then it saves the register. Uh, the trap handler which in C is called, and then based on the extension ID, which is what we said in A7, the SBI processing function is called, which in this case basically console put character. Sends the character to QEMU, and then the QEMU puts it to the send output. There you go. See? That is very nice. This is awesome. I just wrote Hello World from scratch, like actual scratch. Okay, yeah. How long is this video? How long is this stream actually? It's like 30 minutes already just writing Hello World. Think about it. You're spending 30 minutes to print Hello World. That's the art. Okay, the art of low-level development. All right. So I'm gonna push out. Okay, printed Hello World for the first time using OpenSBI device driver. Oh, another one viewing. Hello there. Welcome to our stream. This is a certainly very interesting stream that we have, because we're doing low-level programming, which is my favorite. It's actually my favorite type of programming than any other stuff that I do, because it actually gets me to understand, right, how this whole thing works. It's great. Okay, so we're gonna make our own printf function. Oh my god, this is so cool. Sorry. So, okay, we're gonna make a printf function. We successfully printed some characters. The active item is implemented as printf function. Printf function takes a format string, so print format string, I guess, and values to be embedded to the output. For example, we're gonna implement it just like how you can use it in the C language, right? Where you print like something and then you can add a percent and then a D so that you can put an integer after it, right? Oh, this is great. So, for example, okay, we're gonna do this. Well, printf is bundled in C standard library. It's a rich set of features. Let's start with minimal version. Specifically, we'll implement a printf that supports 3 format specifiers: decimal, hexadecimal, and string. Yeah, this is great. Okay, so since we'll use printf in applications, so let's create a new file. Common.cipher code shared between kernel and user. Okay, so new file. What is it? Common.c. So this will be hello, welcome to viewers, welcome to our stream. Sorry, my nose is a bit goofy. So we will start. First, actually, I think we will write the header file first. I don't know why I like to do that, but because I don't want any import issues. So pragma once. Actually, what the hell is a pragma? I actually want to know. It is a why does it translate to Thai? Compiler is machine operating specific special purpose directed as used to turn off on some features. Okay, so that's an interesting explanation. Okay, fine. It turns on something, right? Okay, so we will define VA list, which is a built-in VA list, apparently. The hell is a VA? Value list? Is that what it stands for? Is it VA and related? I have no idea, actually. Is it value? I think this is add value. Yeah, I think it VA list. Yeah, I think that's what it stands for, does it? I'm not sure. It's alright. And define VA start. We'll add some tab here. Bulletin. Built-in VA start. We have some water. Oh my god, why are there so many people watching? This is crazy. Writing a kernel. Oh, look, there we go. When YouTube with 1 viewer. Yeah, it's my old channel. Hello, welcome. It's a pleasure to have all of you here. I haven't done this in a while, actually. I haven't done this in a while at all. Because, I don't know, I was pretty, not really confident, but hey, I want to do it because I want to spread some goodness to the world, I guess, as if this is any good. Anyway, so build in VA lit end, and then define arguments. Build in VA arguments, and then we're going to define a function that does not have any return value. The return type is void. The return type, which is basically no return, I guess. Well, I mean, it could return something, but there's no like specific like type that it's gonna return anyway. Okay. Let's see if anyone just sends me something. I don't think anyone did. Yeah. Okay. So. Oh, sorry. We're supposed to. It's just a definition. Okay, so this is the actual implementation, right? So we do include common .h, right? And then we put void put character, which is character ch. That's the function parameters, and we actually continue defining the function, which is this. Actually write the function, right? Printf, there you go. And so, let's do this. So, VA list vargs. Actually, what the hell is a VA list? VA is a way for C functions to accept a variable number of arguments. Oh, variable number of arguments. Variadic functions. Oh, alright. I understand now, because these functions receive like different, amounts of number of arguments. Yeah, okay, understandable. Okay, so VA list, these are the variable arguments, and the VA start will be the vargs, and then the formatted string. I think that's what FMT stands for, right? Yeah. So FMT is a format string, and that VA list type to what is it? Is a type to used by functions with varying number of arcs of varying types, right? Cool. Okay. And we shall continue. So there you go. So we will while dereferencing format if this is a while loop, if this one is equals to that. Not sure. Oh, okay. Yeah. Oh, so at the bottom there's a FMT plus, which is basically we're incrementing the, what do you call it? Well, dereferencing FMT, which is basically we're looping through the string, I guess. Yeah, we're basically looping through the string. Yes. That's basically what we're doing. right? Okay, so fnt++, increment format a string, switch case, the apparently this is a skip. This means skip sign apparently. This one is to read next character. So case. Oh yeah, because this is basically deciding. Okay. So this one is reading the format specifiers like %d, %s, or %x. Okay, so case and 0. And then put character. So this is percent at the end. So let's put character, %sign, and then go to end. Okay. If it's a case of a %sign, go to end. I'm not sure why that's not working. Go to end. Is it here? Hold on. Switch. Yeah. Format. Yeah. There you go. Wait, what is the else is the if function. Sorry. Case. Wait, what? If. Oh, sorry. If dereferencing. Wait, no. Wait. What am I doing? It's supposed to be here. Sorry, we already have the if function. Sorry, we already have the if statement. Yeah. Go to end, and this is the %sign at the end of format string, I guess. Put character and then go to end. If case is a %sign, then just print the thing. Because I think this is basically, if it's in a normal string, then just print it out, right? And then just break it. Not sure why it's there, but okay. What the hell? If statement. Yeah. Okay. Next is a case of S. This is gonna be the hold on, let me put this out. Yeah. This is the print a null terminated string. So because this is an S identifier means print a string, right? So we're gonna const character, so a constant character, which is basically a string. We're defining a string again, right? Arg is vargs const char. Yeah, const char string. Yeah, something like that. Because varg is the list of the arguments. Yeah, something like that. And then while we loop through the string, we put the character, which is S, right? And then we S++, and then we break. Oops, sorry, I forgot to put a semicolon there. This is why I left this language. Well, at least the extension that helps me not forget to put it in. Maybe I should put this off because I'm not gonna be using that much things here. Case. Now it's time for D, which is integer. Print an integer in decimal. I think it's from Latin decimalis, decima. I think. Anyway, value is equals to va arg vargs int. Okay. Yeah. And then unsigned magnitude equals value. Oh, interesting. Why do they use this? Why do they use an unsigned magnitude? Interesting. Now implement Unicode. Oh my gosh. That's for later. That's for later. Who knows? I might turn this thing into a crazy thing. Does correctly handle int means representable, whereas int would choose complement machine. Oh, right. Yeah, so this is, we're extracting an integer argument. Yeah. This guy is great. I love this guy. Yeah, so I think this is because it also has to represent negative values, right? Yeah, something like that. Right. Negative values. If the value is more than 0, oh sorry, if the value is less than 0, sorry, then put a character, okay, in front, which is negative. And then magnitude is equal to negative magnitude. Right? And then unsigned so if that's the case, if the statement, okay, if the value is less than 0, then put a negative character in front. That's negative. If the value is -6, put minus and then turn -6 to 6, and then it'll be -6 displayed. Okay, so unsigned divisor equals 1, while the magnitude divided by divisor is more than 9, then the divisor is, what is that? Operator. Oh my god. Operator. Oh, that's copyrighted, isn't it? That is the it is the operators compound. Oh, this is a compound. Yeah, I understand. Compound operator. Basically, take the value of divisor, then times it by 10. That's it. So, how long is the stream now? It's like 49 minutes now. Okay. And then, while the divisor is that, right, and the put character is 0. Okay, this is like if the divisor is more than divisor, and there'll be an explanation. Magnitude divided by divisor. 0 magnitude modulo to the divisor, and then the divisor gets divided by 10, and then we break. right? That is the case for. Why is there a? Oh, my bad. In cases there is supposed to be um curly brackets. My sincere apologies, since that we should follow this actually should be on the second line like that. I do not like it being next to each other. Give it some room to breathe, you know? Okay. Right, there we go. And then for case X, okay, we will actually, I'm gonna put this up here. I think it's more sensible. Not sure why the end part isn't work. Why it says, oh, it's not defined. Is it supposed to be defined in here? It's supposed to be defined, right? Is it? Oh, it's defined down there. Huh. Apologies. Oh, it's supposed to be defined in the print function. No wonder. Yeah. Sorry, VR. Okay. So case X. So this is if you want to print print int in hex. Sades imalis. Okay. In that case, we would do an unsigned value equals to the extract arguments that is unsigned, and we're gonna do another for loop again, as I is 7 and then I is more than or equals to 0 and I is decreasing. Unsigned nibble. That is a very funny sounding type, I guess. This would be I times 4. Yeah. And 0xf. Then put character. Then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, which are the digits of hexadecimal numbers. Actually, I'm sorry. Okay. Yeah, this is great things. We're making great progress over here. We're making a freaking printf function by ourselves. I have never thought that we'd come this far. Okay, so it's surprisingly concise. It is. Goes through a format string character by character. You can encounter a percentage, which look at next character and perform the corresponding formatting operation. As is. For decimal numbers, if a value is negative, we first output. Yep, there you go. We get absolute value. Yeah. Oh, yeah. We're getting absolute value. Yes, there you go. Absolute value. You calculate the divisor to get the most significant digit, and output digits 1 by 1. Interesting. Calculate the divisor to get the most significant digit, and output the digits 1 by 1. We use unsigned magnitude to handle min case. Okay. For hexadecimal numbers, we output the most significant nibble, a hexadecimal digit. So a 4-bit digit, it's a hexadecimal digit, it's the nibble. Let's write that in. Hex hexadecimal digit, okay, which is 4 bits in RISC-V. So here nibble is an integer from 0 to 15, so we use it as an index in the string. Oh, okay. So when you print it, it will print out the number as this. Interesting. I have never heard of that. I just found out. Okay. There we go. That should be everything. We're simply defining these as aliases for the version's built-in prefix. There are built-in features provided by compiler. Okay. Yeah, built-in features provided by the compiler. So let's actually note that down. Built-in prefix provided by the compiler. Clang. Okay, you know what? Let me just copy this reference for in case I were to look at it in the future. Okay, the compiler will handle the rest appropriately, so we don't need to worry about it. Now we've implemented printf. Let's add a hello world from the kernel. Let's go! Let's go! So, what we first do is include the common.h, which is the common libraries that we're using. Oh, someone's watching. Hello. And we'll go to kernel.main over here. And instead of this, we print using printf, our function created from scratch. Okay? We're creating this from scratch. Can you believe that? You know? Can you? Oh my gosh. Okay. Oh, sorry. I just got some hair in my finger. Shit. There you go. Got it out. we just made a printf function from scratch. Okay? Because basically we loop through the string, and then when it reaches the percent sign, we'll see if it's just a percent sign or a what do you call it? What do you call it? A format specifier, right? So let's do it. Okay, so we're gonna do print. Okay, new line, 2 new lines. Okay, and then hello s. Okay, now the s here is the format specifier for a string. So we can type world there. This is similar to how normal C does it, as defined in the ANSI C standard. And then printf, okay, 1 plus 2 equals %d and %xn. And we can write integers. 1 plus 2 is an integer. And then we can write a hexadecimal number as well. 2, 3, 4, A, B, C, D. And then that should be it. Oh, and we also have to add to our compiling scripts. Yeah, there's a reason. There is a reason why they put that. Oh, sorry. Why they put that on the second line, because you can just add more files to it. And then kernel.common.c. So we're gonna compile the C code. Woo! Terminal, where are you? Hello. How do I quit you? I don't know. Control A C Q. Right. Hey! I did it! Look at that! Oh my gosh! Oh my gosh! No way! I actually did! Oh wow! Oh, absolutely amazing! Oh, I don't know how to feel about this. First April. Oh yeah, this is the first stream of the month too. Wow. For 2026 MD, and then we'll put this in. This is our hello world printf. So the hello world printf. Okay, this is the text printed from printf function. Okay, so let's copy the format here. The first April. Happy April Fools. But this is real. Wrote a printf function from scratch. So what this is all about, right? It's basically so it shows what? Now what do we learn from this? Printf is basically putting characters, you know, it's a loop of put character functions being ran. That's it. Oh wow, this is great. I'm not sure if there's anyone commented. No one wrote anything. Yeah. Oh, this is great. I am about to. Oh, look at that! Look at that beauty! Look at that beauty! Oh. Right. Let me comment that. Yo! Just implemented a printf function from scratch. I am so happy. Confetti. See, this is what we call the art of programming. This is the art. Okay? You learn how things work. Okay? Where's the screenshot? You learn how things work by building it from scratch. This is the art. The art of it. Oh, wow. Kernel, low level. Alright, I will push this. Implement it. Printf function in common.c. We did! And I will copy the actually, let me look at it on my GitHub. There we go. Yeah, there you go. That's the commit. Hey, we did it! We did it! Guys, we just made a printf function from scratch. Oh, I'm so happy right now. This is great. Okay? This is great. Oh, wow. I'm crying. Well, that concludes it for today, as we have just created our own printf function from scratch. That is the art programming. Oh, wow. Oh, I am crying. I am about to cry. Oh, wow. Look at that. Now my code is on GitHub. Yeah. Oh, wow. Alright, well, that'll be the end of our stream. Thank you very much for watching. There will definitely be another stream tomorrow because I will continue to do this every day because it's part of my assessment as well. But this is what you make your assessment fun, yeah. By doing this is great. So hope to see you guys tomorrow. I will see you tomorrow next time. Thank you.